probably we can just start or
whatever works for you.
Okay.
I'm free.
这个孙宇或者是那边你们是觉得我们现在就开始可以吗？
开始录了吗？我这也是录制。
你们准备好了，我们就开始。
那开始可以。
可以了。咱们得静音吧？
对，你们几个静音。Okay. Yeah. So great. Let's get started. And I am the host, and CE will ask you questions. Okay. So we start to understand our universe ever since the very early days of our civilization. For example, in China, we have yin yang and wuxing conjecturing about the fundamental features and building blocks of our universe. And we have Tianren Heyi questioning the unification of the internal and external world. Ever since our ancestors looked at the night sky, we are curious about the stars, curious about our universe. Now with modern science, we have understood much more of our universe. But still, there are so many questions, such as how the universe started, how large our universe is, how life started, originated from the Earth, or anywhere in our universe. Are there aliens? Are there parallel universes? To address these questions, knowns and unknowns, it's our great honor that we have invited Professor Lemon Page from Princeton University. He is one of the original investigators of WMAP, which is among the most important cosmology experiments in our times. He has got the Shaw Prize, the Breakthrough Prize in Fundamental Physics, and many other prizes. In addition to his great achievements in research, Lemon also made great contribution in popular science. His popular science book, The Little Book of Cosmology, 宇宙小史, has recently been translated into Chinese. I'm fortunate that I have read a preprint version of the translation. The book is just wonderful. It's
Thank you.
Great. It's great that it's going to be published in China. So let's get started from this book. So Lemon, would you briefly introduce your book? Which part of your book do you think is most interesting?
Oh, wow, thanks. Okay, so I think maybe the most interesting and important part is the message that we can really know our universe through measurement. And you talked about our forefathers, the ancients, looking at the night sky and wondering. And what has happened, and especially in the last couple of decades, is science has advanced and our understanding of the universe has advanced. And we've been able to marry instrumentation with theory and observe the new universe in new ways that were unthinkable half a century ago. And so we can really look at the universe at its grandest scales through measurement. So this isn't speculation, right? This is, we can really measure things and then test models, find new things, and go from there. So I think in the book, I try to just sort of unwrap that picture and show how that works and how simple it really is, how you can really put it together, how you can sort of now imagine looking out in the universe like our forefathers would be looking out to further and further planets, except the scale is much bigger, the instruments are much more sensitive. So.
Yes. Yes, that's really wonderful. Yeah, actually, as a theorist, since I'm a theorist and when I'm reading, I actually learn a lot from how really we understand from observations. Because previously, a lot of things just the observer, like you, tell us numbers, okay, and we trust these numbers. And now we understand much more about these observations.
Yeah. Oh, thank
and
you.
I hope that the reader who read your book really understand how we understand our universe. Yeah, that's really important, really important. Yeah. So let me also introduce our guest, CE Zhou. She's going to discuss with Lemon about our universe. She's a postdoc from Kobe University working on string theory and cosmology. She's also very famous for her popular science videos. So CE, would you start with your questions to chat?
Yes, since for my fans and a lot of them just started like they are little kids or something, and maybe they need some background knowledge. So would you like to first have a brief introduction about what is the cosmic microwave background and what is the history of the development of cosmic microwave background and how it helps us to kind of shape our understanding of the cosmology?
Sure. So this radiation was discovered by accident by Penzias and Wilson in 1964, actually not too far from where I am right now. And what they did was they looked up at the sky. They were trying to develop a way to communicate with satellites. They looked up and they saw there was this radiation that was uniform throughout the sky. And so when they were looking in the microwaves, that's why it's called the cosmic microwave background. And they were looking just at one frequency. But even then, if you have one frequency with a small bandwidth around it, you can ascribe radiative intensity in terms of a temperature. So they figured out that this radiation corresponds to about 3 degrees above absolute zero, so minus 270 degrees Celsius. And it was recognized because it was so isotropic, it's the same all around, that had to be cosmic in origin, right? There are no hints of the galaxy in it or anything like that. And there have been models around that said this radiation should exist. Gamma and Alpha and Herman had some models, and Bob Dickey had put out some models too. And so this had an immediate interpretation as cosmological. So what is it? So I said it's sort of like very cold radiation now. And just to put that in perspective, right, if the sun in the same units is about 6,000 degrees, and you can feel radiant energy from the sun, right? But now if it's 2,000 times colder, you're not going to feel much radiant energy from it, right? So it's very cool radiation. And so the picture is that it came from a time when the universe was much more compact and much hotter, much denser. And then as the universe expands, it cools, expands and cools and expands and cools. And now this radiation, which was once intensely hot in the very early universe, is now cool. It's now 3 degrees above absolute zero. And as the universe expands, it will continue to cool down. It will just get colder and colder and colder. And so this is Penzias and Wilson and then many others made measurements for years to confirm that it corresponded to something that was, quote, thermal, that it radiated like, a hot oven stove or like a kiln or something like that, that it had very specific properties. And it looked uniform. It really looked uniform, but everyone knew that there had to be tiny variations in its temperature, just from spot to spot on the sky. Or I should say we hoped, right, if all the models were right. And there had to be those variations because our notions, of the universe were that if it started off in a hot, dense state, fairly uniform, right, everything was in a cauldron, and expanded and cooled. But when we look up today, we have stars and galaxies and clusters of galaxies. So those had to have their seeds, the seeds of formation somehow embedded in this radiation. It wasn't known how, but it had to be the seeds of the cosmic structural formation had to be embedded in this radiation. So there should be tiny variations. And really no one knew the character of the variations. There are a few models. And finally, the COBE satellite discovered them in 1992. And then what a group of us around the world have been doing since is trying to characterize those variations. And then through characterizing them, we can really learn how the universe began, what it was composed of very early on, and how all the structure in the universe formed. So that's a very compressed view of what the book goes over, but that's sort of the basic idea. So it's that we're looking at this again, looking at this ancient radiation, like we're looking at a fossil, right? We're looking at a dinosaur footprint or something like that, and figuring out what the universe was like very, very early on.
Yes, and you mentioned that there are the first one is Penzias and Wilson, and then people use Colby and then WMAP, and then there are several generations of telescope have precision measurement of a cosmic microwave background. And since I am a theoretical cosmologist, I don't know some details about. Can you tell us how people improve the experiments? Like why they can have more and more precision measurement, and from like how do they upgrade?
Okay, Kobe. So
yes.
So you can one way to think about it, if you look at the WMAP satellite, say, you know, so there are a couple of elements to it. One, it looks like two back-to-back TV satellite dishes. I mean, and that's because the measurement is a lot like a TV satellite, what a TV satellite dish does. And there are two to look at, because we want to look at two different parts of the sky, and we want to look at their difference, right? These are the tiny temperature differences that we want to measure. So we look at two skies, look for temperature differences. And so what's happened over the years is just our ability to understand how that kind of telescope works, while at the same time improving the sensitivity, and just how those work together. Because I can sort of give you the challenge, you know, give you a picture of the challenge, right? This radiation is about 3 degrees above absolute zero. In the same temperature scale, the Earth is roughly 300 degrees above absolute zero. This is all the Kelvin temperature scale. And these measurements are seeking variations of a part in 100,000 of 3 degrees. So looking for tiny, tiny temperature variations. And, you know, and of course, we're trying to measure them to percent level accuracy. So these are tiny, tiny temperature variations. And here you are sitting on a very, very hot Earth, right? And we're trying to measure these tiny temperature variations. It's like sitting in your room, right, and looking at the wall and trying to tell if one spot is 100,000ths of a degree hotter than the other spot. So it's as much sensitivity as it is control of systematic errors. And so the evolution of the field has been first this measurement. You know, Penzias and Wilson made it with, by today's standards, of course, simple instruments. And then it's really been this evolution of understanding how you do the measurement and making more and more sensitive instruments. So for instance, now, I'm part of an experiment in Chile. We use thousands of detectors cooled to 1/10 of a degree above absolute zero, just because we're really pushing the sensitivity. And so those, you know, these didn't exist 2 decades ago. So it's just, so we've sort of gone from, you know, sensitive, like these like coherent receivers, which was what WMAP was, like a TV dish, very much like a TV dish, to now much more numerous sensitive detectors on the ground. So sort of the state of the art now are experiments with 5,000 really, really sensitive detectors looking at this radiation and measuring it on a day time scale with what WMAP could do over its lifetime. So again, it's this combination of, it's not just one thing. It's not like someone invents a laser or something. It's just this constant interplay between understanding instrumentation, better detectors, understanding better detectors.
Yeah, you mentioned that this Penzias and Wilson measured one frequency, and later I think the other experiments have kind of multiple frequencies to measure. So I really wonder how people choose what kind of frequency range they should measure.
So yeah, so if you're on the Earth, you choose frequencies where you can peer through the atmosphere. And it's just because there's fortunately there's oxygen and there's water in the atmosphere, but they emit in certain lines, and we choose the frequency bands so we can look between the emission lines. So for instance, oxygen, anyway, we look on the ground, it's mostly there are two oxygen lines and a water line, and we look at, I should say, frequencies or wavelengths between those. They're all around a few millimeters wavelength of radiation. If you're in a satellite, of course, you don't have to worry about the atmosphere. So there, you choose a bunch of bands, and we all choose numerous bands, frequency bands or wavelength bands, because we want to make sure that we can extract the cosmological signal from a signal in our galaxy, right? It's as though there's, in our galaxy, there's a lot going on. There are electrons whizzing around, and there's dust emitting energy, and there's, there are various lines, all sorts of things like that. And we have to make sure that we're looking past all that. And the way to look past it is to measure in multiple frequencies and then ensure that the frequency spectrum that you're looking at is that of what's called black body radiation, which is the thermal radiation of the cosmic microwave background.
So the main point is confirm this black body spectrum. If we choose multiple band to measure, we can kind of confirm this black body radiation.
Yes, both for the temperature itself, and for the fluctuations. They both have to have that spectrum.
Yeah. So the main difference of the ground-based experiments and the space experiments is that ground-based experiments, you have a kind of preferred frequency band that is influenced by the atmosphere. So only a certain range is beneficial.
Yeah, that's one important element. The other is that there's, as I was mentioning systematic errors before and trying to make a really precise measurement. That in space is extremely stable, right? There's no weather, of course. And so you have to design your instrument to take advantage of that. So you can just keep averaging data for day after day after day after day without touching anything. Whereas on the ground, of course, the day and night, unless if you're in the Antarctic, it's one thing, but there's weather and all sorts of things happen. So your data always gets broken up, and you have to cycle your instrument, all those sorts of things. So space is much more stable. And that's why, for example, when you see maps of the microwave background, all the largest angular scales are measured from space and measured best from space. So if the big picture is always from space. But as you get to finer and finer resolution, those are best measured from the ground. And it's just because from the ground, just again, sitting in your office, right? If you look at one side of your office and you look at the other side and you're trying to tell the difference in temperature to 100,000th of a degree, you're just not going to be able to do it, right? There's too many other things if you look in opposite directions. So in the ground, so you really have to go to space to get to be able to look at these large separations.
So you mentioned that the space that has the advantage of measuring large scale kind of fluctuations on the CMB. The ground-based experiments are more beneficial for the small-scale kind of measurements. And could you tell me or tell us more if there are more kind of pros and cons if you compare the space-based experiments and the ground-based experiments?
So the ground-based experiments are less expensive. And you can advance technology more rapidly because you can go there and fix something. But space, you will, from the ground, you'll never achieve the stability of space. And the angular scale range. So I really, those are the main things. It's control of systematic errors is really excellent in space. It's hard to compete. But we have to keep measuring. We have to learn more and more. And so I think if we could measure large angular scales from the ground, we would. If we could easily take all these thousands and thousands of detectors and put them on another satellite in short order, we would. But right now it's just much easier and much less expensive, and you can make scientific advances much more rapidly by working on the ground. Mm-hmm. There's another element too, and that is that the microwave background is polarized, which means you have Polaroid glasses, right? You can if you look through polarized sunglasses and you tilt them, and you can take them off, tilt them, and look at them, what you see looks slightly different because light, especially glare, say from the hood of a car, is polarized. This just means that the electric field is vibrating preferentially in, say, that direction versus that direction. And what the Polaroid glasses, what they do is it's like light going through a fence or something. They let one polarization through and they block the other one. Okay, and actually, if there are a set of wires, it's this one they block and they let through that one. But it's a detail. So we look at the sky. All these experiments now are looking at the sky and quote polarization. And the nice thing about polarization is, to first approximation, it's independent of the temperature of the atmosphere. So even though the temperature of the atmosphere might be fluctuating above you, and even in the best sites, it goes up and down by a good fraction of a degree. In polarization, it doesn't, because you take one direction of polarization and subtract the other and look for that difference. And so you can really take advantage of the ground there. And even using that technique or that approach, you still can't get to the very largest angular scales easily. The sky is still, it's still hard to do that from the ground. But we can look at a lot of other angular scales. So I'd say all modern experiments and all proposed satellite experiments have polarization as a key, as the key element, the key feature. And I just want to take a step back and go back to this idea of our model and how well we know the universe. And this is just, it's all happened within my career, for example, is we've gone from not measuring this radiation, not measuring the radiation, not measuring the fluctuations in it, to looking for variations in the polarization that are tiny, measured in nanokelvin. And it's just been this steady advance and the interaction with interpretation. And what's amazing, and I should have said this, the second element of, what's to summarize the picture is not only can we measure the universe, we have a model of it. And it's very simple. The universe, when it was young, was very simple. It's sort of 6 parameters and a couple of processes can describe everything.